Hello everyone, my name is Nishant Yadav and I am a computer science student from San Jose State University. Today I will be presenting my project on the topic MultiMap implementation in OpenJDK. This work was done under the guidance of Professor Robert Chun from the Department of Computer Science at San Jose State University. Let's dive into the agenda for today's presentation. Our agenda for today includes the following topics. We will first discuss the background of the project, then we will move to the project goal, we will discuss the implementation details, and we will discuss some use cases. After that, we will discuss some of the experiments conducted, and finally, we will discuss the conclusion and the future work. Let's start with some of the background information. Let's first discuss what a key value pair is. As we can see in the diagram, a key value pair is an elementary data model where each unique key is associated with a value. This key and the value can be of different type. Each can hold a different value, but the condition is that each key should be a unique value. This model allows for quick lookups and have a number of applications in computer science. Now that we understand what a key value pair is, let's discuss some of the most common use cases of key value pairs. Key value pairs are used extensively in data models within programming languages. Some examples include map data structure in Java and C++, and the dictionary data structure in Python. Key value pairs are also used in NoSQL key value databases. It is also used in popular cache solutions for quick data retrieval, configuration files in projects for storing settings, and for managing session-related data in web applications. Now that we understand what a key value pair is and its use cases, let us discuss the data structure implementation of map in Java. A map data structure consists of unique keys with corresponding values that can be duplicated. Common implementations include hash map, linked hash map, and tree map, each with specific features tailored to the use cases. As shown in figure, each key is hashed using a hash function to get the value stored corresponding to that key. Now, let's discuss some of the features of map data structure in Java. The maps in Java offer fast lookups, generally in constant time, and store a single value for each key. The keys should be unique. The most commonly used methods include the put method, used to put a value associated with a key in the map. The get method, which can be used to get the value from the map based on the key. And then contains key method, which can be used to check if a key is present or not in the map. These are useful in configuration files, caching data, and handling request parameters. Next, we will discuss different implementations of the map interface provided in Java. The three implementations are HashMap, the linked hash map, and the tree map, each having unique features as per their use cases. The hash map does not maintain any order of elements inserted into it. The linked hash map preserves the order of insertion of elements, while the tree map keeps the keys sorted according to their natural order or a custom order provided using a comparator. Now that we understand what a map is, its different implementations in Java, and its unique features, let's discuss what a multimap is. A multimap is an extension of the map data structure and, as shown in the diagram, allows associating multiple values to a single key. Unlike traditional maps, the value in a multimap is a collection, making it more versatile for certain applications. Some of the existing implementations of the multimap include multimap implementation in the standard template library of the C++ language and the Google Guava library in Java. However, OpenJDK does not have an inbuilt multimap support, which leads us to the goal of our project. The goal of this project is to implement MultiMap in OpenJDK and to create a custom version of OpenJDK. This will allow developers to write cleaner and more concise code while evolving the data structure to fit their needs. OpenJDK is an open source implementation of the Java Standard Edition. It includes the core Java programming language, the runtime, and the libraries. Our implementation aims to enhance and create a custom-built version of OpenJDK having the support for MultiMap in the utility library. There are certain requirements which are need to be fulfilled to build a custom version of OpenJDK. These are mentioned below. For the operating system, we have used macOS. For the compiler, we have used the CLang compiler for macOS. And interestingly, we need an existing version of OpenJDK installed on the system to build a newer version. This is called the boot JDK, and for this we have used JDK 19. Now let's move on the specific implementations of MultiMap done in this project. The diagram below shows the hierarchy of the implementation of MultiMap in OpenJDK done in this project. MultiMap is implemented through an interface and several classes. The interface defines method signatures, while abstract and concrete classes provide specific functionalities. We will look at these in more detail in the coming slides. Next, we will discuss the implementation details of the MultiMap interface in the hierarchy. The interface provides us with some basic method signatures which are used for performing different operations on the MultiMap. These operations include querying operations, modification operation, bulk operation, and views. The interface itself sets the foundation for different MultiMap implementations. The operations which are provided by the interface include the size operation, which will return us the size of the multimap, the isEmpty operation, which checks if there are any elements in the multimap or not, the contains key and the contains value, which will check for a key and a value respectively in the multimap, the get operation, which gets us the values associated with the given key. Next are the modification operations. These are put and remove, which allows us to insert and remove keys from the multimap. The bulk operation is the clear, which allows us to remove all the data stored in the data structure at once. It also provides us with three views: the key set, values, and entries, which will be discussed further in detail. The abstract class, abstract multimap, implements the interface multimap and provides us with the method definitions and variable declarations. It leaves some of the methods as abstract, which would be implemented by the different multimap implementations. This class also handles different views for the multimap and provides variables to store these views. Now we will discuss the ArrayList multimap class, which extends the abstract multimap class and implements the multimap interface. It uses an array list to store the values associated with each key. It allows us to store multiple values, but duplicate values are not allowed. The insertion order for the values is maintained in ArrayList multimap. Finally, it provides us with two types of constructors, a default constructor and a parameterized constructor. As shown in the diagram below, ArrayList multimap provides us with two kinds of different constructors, a default constructor and a parameterized constructor. The default constructor is an easy way to create an instance of the ArrayList multimap. The parameterized constructor allows us to specify the size of the multimap and the values which should be associated with each key. Next, we will discuss the setMultimap class, which extends the abstract multimap class and implements the multimap interface. The setMultimap uses a hash set to store the values. Hence, it does not allow us to store duplicate values associated with a single key. The insertion order of the values is not maintained. Again, the set multimap provides us with two kinds of constructors, default constructor and the parameterized constructor. As shown in the diagram below, the default constructor is an easy way to create an instance of the set multimap. On the other hand, the parameterized constructor can be used to specify the size of the multimap and the values which should be stored against a given key. The tree multimap is the final implementation of the multimap, which we will discuss. Again, the tree multimap class extends the abstract multimap class and implements the multimap interface. It uses tree set to store values and hence does not allow duplicate values. The keys and values can be stored in a sorted order or a custom order which can be provided using a comparator. Again, it provides us with two types of constructors, the default constructor and the parameterized constructor. As shown in the diagram below, the default constructor is an easy way to create an instance of the tree multimap. For the parameterized constructor, we need to provide it with a key comparator and a value comparator. These will be used to store the keys and the values in the order which the comparators specify. This diagram shows us several methods for querying, modifying, and bulk operations which are provided by all the three implementations of MultiMap. These methods ensure that the multimap can be used effectively in various applications. Next, we will discuss different views which are provided by the multimap. These views provides us the data stored in each multimap in different forms, hence allowing us in the aid of handling data and its manipulation. The key set view provides us with a set of all the keys which are present in the multimap. The values view provides us with a collection of all the values stored in the multimap. The entries view returns a collection of mappings of key and value pairs stored in the multimap. The keyset method returns a set view of the keys, allowing us easy iteration and manipulation of the keys in the multimap. Here in the example below, it shows us how the keyset method can be used along with its output. In the screenshot below, it shows us all the keys stored in the multimap. The values method provides us with a collection view of all the values stored in a given multimap. This is useful for operations that need to process or analyze the values collectively. In the diagram below, it shows us the example code and its output. In the screenshot, we can see that it returns us all the values stored in the multimap. The entries method returns a collection view of the mappings, that is, the key value pairs stored in the multimap. This is particularly useful for iterating over and processing the entire data present in the multimap. As shown in the diagram and screenshot below, the code to get the entries from a multimap and the output which shows us that each key is associated with a single value. Now that we understand what a multimap is and we have discussed its different implementation, let's take a look at different use cases which can be handled using a multimap. The first one is graph algorithms. We can easily use a multimap to store a graph and an adjacency list representation. Next, we can use multimap in statistical analysis for frequency distribution and histograms. And finally, we can use a multimap to store geographical data, and we can use a tree multimap to sort the geographical data based on distance. Finally, in this section, we will discuss some of the experiments performed to compare the different implementations of multimap. These experiments consist of a comparison of the execution time of various operations performed on different implementations of multimap. Mainly, We would be comparing the time taken in the insertion operation with a different number of keys and data types. For each set of experiments, we perform 10 runs with random values and have considered the best case out of the 10 runs. The graph below shows us the experiments performed on ArrayList MultiMap. The left one is for integer data type and the right one is for float data type. In the graph, the blue line represents the Goa implementation of MultiMap, the orange line represents our OpenJDK implementation of MultiMap, and the green line represents the C++ implementation of MultiMap. In the left diagram or graph, we can see that the C++ implementation performs significantly better for each count when compared to the other two implementations. Since the goal of this project is to provide a new implementation in OpenJDK and in Java, for further experiments, we won't be comparing it with the C++ implementation of MultiMap. In both of the graph, we can see that our implementation of MultiMap in OpenJDK performs better when compared to the Java implementation of MultiMap. Continuing with ArrayList MultiMap, here are the insertion times for the string data type. We can see that the Java implementation of MultiMap performs better when compared to our implementation in OpenJDK. The graph below shows us the experiments performed on set MultiMap. The left one is for the integer data type and the right one is for float data type. We can see that our implementation of MultiMap in OpenJDK performs slightly better when compared to the implementation of MultiMap in the Java library. Here are the results for set MultiMap with the string data type. Observing these times, we can see that our implementation of MultiMap in OpenJDK performs a little worse when compared to the implementation of MultiMap in the Java library. Finally, the graphs below shows us the results for the experiments performed for tree MultiMap. The left one is for integer data type, the right one is for float data type. We can see that our implementation of MultiMap in OpenJDK performs slightly better than the implementation of MultiMap in the Java library. At some places, they even perform quite similarly. The last graph represents the experiments done on tree multimap using string data type. From the graph, we can see that our implementation of OpenJDK performs slightly better when compared to the implementation done in Java. Even both of the implementation performs similarly at certain number of key value pairs inserted. In conclusion, we have successfully implemented support for multimap in OpenJDK. A multimap allows multiple values to be associated with a single key. This implementation will help in saving developers' coding effort, allowing them to maintain clean code. This custom version of OpenJDK would be a valuable addition for developers. Finally, we will discuss some of the future work which can be done in order to improve this project. The first one is trying to improve the performance of complex data structures such as string in the custom implementation in OpenJDK. As we have seen in the experiments, the Google Guava implementation of MultiMap performs better for string data type when compared to our implementation in OpenJDK. We can further go ahead and add additional operations or methods to perform on the multimap as per requirement, which would allow us to manipulate data in different forms. Finally, we can try to develop a key value data store with the support for multimap, since we have seen that it is a really important data structure and would significantly save developers' efforts. This is the end of the presentation. Thank you for listening. Have a nice day.